for our next bit, we're going to skip a bunch of pages. So, skip this page, skip these pages, we're on this page. This one right here. But real quick, before we actually do anything, look at the next page. See this table? This really big table? Ugh, it's a horribly large table. But we're just going to need to look up values for Ka, just so you know. You shouldn't know what we're talking about yet, but we're going to get there. On this page, go ahead and just cross out. See these guys? See all these guys? Look at this. I don't even want to think about 4 through 6. Gross. We're only really going to be doing these here, okay? But before we get to that, we need to talk about weak acids. All right, I mentioned weak acids, but I mean, what's a strong acid? Let's think about it this way. If I've got something like, let's say, hydroiodic acid, HI, its hydrolysis reaction looks like this. That is just going to happen. It's just going to go. Once that hits the water, this is going to disassociate, and it's going to be perfectly comfortable existing like this. So our concentration of hydronium ions, this concentration right here, H+, is equal to our concentration of that initial stuff that we added. Now that happens because, remember back to atomic structure, that we have different atomic radiuses? Well, iodine is huge. It is one of the larger elements. So if I've got some iodine floating around, its electron cloud is massive. And it's able to take that little negative charge and kind of distribute that all throughout this really large cloud. It's perfectly comfortable existing like that. In fact, when it's in water, it's going to get surrounded by water molecules. Those are going to just kind of escort it. It's basically acting like a celebrity. But what about something like hydrofluoric acid, HF? This is also going to dissociate to H+ and F-, but that F- is a very tiny atom. It's also the most electronegative atom. It is ultra greedy to grab some protons. So if this guy is floating around in a solution, just moving around here, and it encounters an H+, it's going to grab it right up. It's going to be better at grabbing that H+ than any of those OHs are. So when hydrofluoric acid gets put into water, not all of it breaks up into these two ions. So what we're saying is the concentration of HF does not equal the concentration of H+. And in fact, most acids are weak acids. They will not fully dissociate. And because of that, we're going to have a lower concentration of H+, so our pH is not going to be as significant. It'll be closer to 0 or closer to 7, closer to neutral than we would expect. So we're not able to just figure out the concentration of hydronium ions directly. That's where these tables are going to come in. This table right back here, this table right here has this value of Ka. What is Ka? Well, there are a lot of reactions like this, where they don't just go in one direction. So we actually have, if I've got HF dissociating to H+ and F-, at the same time, in the same solution, I have a bunch of H+ interacting with F-, turning back into HF. So this reaction can actually go both ways spontaneously, right? Think about that word, spontaneous. You know, if we had something like methane being burned, it would turn into carbon dioxide and water. That's spontaneous. It goes in one direction. Once it's burned, it's burned. We can't redo it. It's like trying to take a candle, light it, and let it burn all the way down to the bottom. It's not going to come back. It's not going to spontaneously, all on its own, collect from the atmosphere all the parts that it made and become a candle again. That's not going to happen. But this is. This is going to go back and forth. We're going to have hydrofluoric acid turning into hydronium ions and fluoride ions, and we're going to have hydronium ions and fluoride ions getting back together. It's like the couple that keeps breaking up and getting back together over and over and over again. It's like everyone wants to say, guys, you just don't work, but they just can't seem to learn their lesson. It's the same way. Fluoride cannot seem to learn its lesson. That hydronium is a bad egg. Girls, stay away from that guy. So, when we have this situation, the way we write that is HF, and then we're going to put arrows going both ways. We call this an equilibrium because there will be a point where it's going this way and that way at the same rate. And so we'll have some amount is going to be the HF and some amount is going to be the H plus and F minus. The way we're actually able to figure out that point is every one of these reactions has a different ratio where they're going to be satisfied. When we say ratio, I literally mean a mathematical ratio. I'm going to take the concentration of H plus, let me see that? Okay, good. H plus times the concentration of F minus divided by the concentration of HF. Boom. That ratio is going to be a unique value for hydrofluoric acid. And that's going to equal a constant. So anytime I have hydrofluoric acid, it disassociates according to this ratio. And that ratio is represented by this constant. So Ka. Ka, A for acid. We could have Kb for bases. Ks is that same kind of ratio for solubility reactions. So these actually permeate. This would really be the next step in chemistry that we'd look at is reactions that go back and forth, and how do we know where they'll end up? So this hydrofluoric acid is going to have a unique ratio of how much it's going to break apart. And that is what we would find in this table. So I could look down and go, okay, I need HF, and that is, I probably already passed it. I don't know where it is. There it is. Okay. 6.6 times 10 to the negative 4. So that Ka equals 6.6 e to the negative 4th. There we go. Now, a different acid is going to have a different amount. So if I had, let's say, well, let's just say, when the number is really large like that, that's how you know it's a strong acid. So look at that. Hydroiodic acid, that number is massive. So it's basically just all going to disassociate. HClO4 for chloric acid, just large. We don't even need to know the number. It's a strong acid. So those will just disassociate completely. But then something like, let's grab, hey, how about methanoic acid? I like that one. Let's do that one. Methanoic acid. So that's going to have the same thing. Let's draw a dotted line here, and then it's going to be HCO2H. Okay. HCO2H. So when that disassociates, it's going to have an equilibrium going both ways, and it's going to break up into an H plus and a CO2H minus. Okay? So we could figure out the constant for that reaction as well. That would also be H plus times CO2H minus over concentration of HCO2H equals Ka, and for that one we get 1.8 times 10 to the negative 4th. So that Ka equals 1.8 e negative 4. So you see those are different numbers. So those are going to disassociate by a different amount. So in fact, whatever. Okay, so that's all we need to go over for today. You don't have anything to do in here yet. Tomorrow, just watch this video a couple times. Tomorrow we're going to go through how to calculate the pH of a weak acid using that dissociation constant.